I'm going to be talking today about electrical enclosure design with simulation and how simulation can be used to really simplify that process down. Additionally, as you mentioned, we've got me who will be presenting all the material here today, but I've got my team of experts behind me. That's Troy, who's a senior CFD consultant, Brandon, who's an FEA consultant, and Adam LeMay, who's an FEA application engineer, all at RANSIM with a specialty around electrical enclosures. So they're here to help answer questions that you may have, so don't hesitate to drop those in the questions box so we can make sure to get those answered at the end of the presentation today. But diving into things, I'm going to cover a little bit of an agenda of what we'll be going through today. So we'll start out with just an overview of what are electrical enclosures, followed in with the role that simulation plays in electrical enclosure design, really how it's used, what the value is, and following that, diving into the specific items that we often use simulation for. So that's going to be more tailored towards the exact physics phenomenon or issues you run into with electrical enclosures and why you care about using simulation for that design. Followed on by then a case study that really culminates all that information in a more applicable format, showing the actual use case of the software for a specific electrical enclosure design there. And throughout the presentation, you'll see a bar at the bottom that shows where I'm at within the presentation, so you can follow along a little bit with the ideas that I'm going to be coming in with that relate back to the agenda there. But as mentioned, starting out, I'm going to go over a little bit of an overview of what exactly are electrical enclosures, where are they used, the likes. So electrical enclosures, as I'm sure you can imagine, are enclosures. This could be a plastic, metal enclosure that have electronics embedded within. So most often this looks like a PCB with a couple components on it. And really these electrical enclosures are used across a very wide array of industries and applications. I mean, you see them all the time in data centers and BESS systems, right? At the end of the day, a computer or a server sitting there in a rack is an electrical enclosure in itself. But you definitely see it in industries past that. You see it in manufacturing, defense, transportation, and out and broad beyond that for even toys, if you could think of it or extrapolate to that, right? And at the end of the day, for each of these industries and applications, while that electrical enclosure looks very different in practice, and it obviously has different design conditions that you're looking at for them, they all fall back to those same exact functions. And they're really becoming a lot more prominent within the engineering space. As we move towards reliance on automation and onboard sensor integration towards processes. So you could think of a manufacturing line that's got an optical sensor for quality assessment, or a data center that's packed with these units that are processing information rapidly, and they need not only to do so effectively, but also have a controlling unit that manages them, or in your vehicle, the electrical enclosure that's going to be managing all the sensors on board that help with automated driving, lane assist, or even when to turn your lights on and off, right? There are electrical enclosures, there are PCBs, components that dictate a lot of that. And at the end of the day, a lot of the design within electrical enclosures falls back to one very critical principle, which is that all of these components embedded in electrical enclosures generate heat. They generate thermal energy as they're used. And the more they're taxed, typically the more thermal energy they're going to be dissipating. So if you have a GPU that's processing 24/7, it's going to be dissipating a lot more heat than if you just have an onboard LED or a simple component that's managing current through another device, right? And so there's a wide array of what you look at with these, but at the end of the day, because of their prominence and how much more common we're seeing them and the reliance on additional computing power, we're seeing more and more demand of these, and the demand then drives additional thermal generation within these components as they scale up and become more powerful. And as a consequence, they need better management, right? If you don't manage that thermal energy, you can run into a wide array of issues, from devices failing to seeing reduced lifespans, the likes. And why we care about electrical enclosures at the end of the day, the value behind them is, as I kind of mentioned prior, that they drive a lot of the new and innovative engineering initiatives that we're working towards. So that could be automation, onboard sensor design, telecommunication availability. So you don't want to necessarily run a couple hundred feet of cabling across a massive warehouse to 25 different sensors. You want those to be able to communicate natively over a Wi-Fi channel, let's say. All those things are going to require their own type of electrical enclosure. It's going to have components that are generating heat with it, and all of that needs to be managed. And so because electrical enclosures inherently have a value driven towards the product itself, right? A lot of these products that are being developed aren't really innovative products without the electrical enclosure, without that automation sequence or that onboard sensor or whatever it may be. Their value is self-driven, and as a consequence, their design really needs to be taken with care. If you have that electrical enclosure fail, sometimes it means the entire failure of a product because it relies on that electrical enclosure for its behavior scheme and the value that it provides. And so when we're looking at these designs, oftentimes we're trying to figure out how we can manage that thermal energy, how we can make sure that PCBs operate reliably, things like that. And the areas that simulation really comes into that process is making sure that you can understand those thermal risks, making sure that you know how your product will be performing from a reliability standpoint, understanding the potential lifespan without having to dig in and do arduous physical testing, especially in early prototyping stages. And so the value that simulation brings to these enclosures is that it gives you some unique insight and data into those designs, either during or before prototyping stages, right? You can, for example, with fluid flow, you can visualize where that fluid is moving, and you can see that in an image on the right to see how much fluid might be circumventing your heatsink, right? The heatsink's goal is to extract thermal energy from a component and dissipate it to the air streams. But if most of your air is moving around that heatsink because there's too much of a pressure resistance for air to move through the heatsink itself and extract that energy, it's not going to be operating as efficiently. And when you do physical testing, it's not always as easy to visualize some of those things. Yes, you can do smoke testing, but sometimes it's a lot more difficult. It requires a lot more care in those experimental setups than running analyses, which can really give you a lot of that extra insight. You could see the same exact thing for a drop test, for example, right? You take your product, you drop it, the output of that drop is likely you're going to see a fracture, a crack, or some failure of sorts. And while you know where that crack or failure is, you don't always know what led to that occurring, right? What deficiencies within the structure actually led to there being a lack of support in that region, because the failure isn't always at the point of contact initially that you're concerned about, right? It might be residual damage to a PCB or a solder joint. And simulation can really help you understand and visualize that. So it's a little bit less of a guess and check game and more of a targeted figuring out exactly what's going wrong and addressing those specific components. Additionally, it can make sure that when you're evaluating products, you're not only evaluating them for the everyday scenario, that normal exposure condition, but also worst case designs, and being able to easily do so without having to completely rebuild your product, right? If you keep doing drop tests and seeing failures with a prototype, you're having to remanufacture or fix that prototype every single time it sees a failure. Whereas in simulation, you can quickly iterate through even hundreds of different drop scenarios or prototype styles quickly without the need to go back to the drawing board and fix up your original design or recast molds to change how your enclosure is going to look, right? So it allows you to do a lot of that worst case design in an expedient fashion without the reliance on moving back to a constant build and test environment. And lastly, because of the ability to evaluate that worst case condition and give you that unique insight, you can reduce the risk of product failures at the end of the day. It gives you that insight into what exactly is happening from a physics perspective, so you can address all potential adverse events that your product may be exposed to, and use that to move your product towards not only product reliability, but efficiency. So you don't need to over-design components, or you can make sure that your system will go in and when it's being spec'd out to meet specific requirements, have that guarantee that it will, because you've analyzed the system going into those conditions for that spec requirement. So it could be MIL standard 810 or any other requirement you may have on your electrical enclosure. And so simulation really provides value in giving you that additional insight, letting you move through iterations quickly. And you can do that at any point in the product development cycle. You could do it before you even come into your full concept solution that you're looking towards. You could do it in the middle of prototyping to make sure that you're only prototyping the top 4 candidates as opposed to 100 candidates there. Or even after your product is almost to the finish line and you just want to get that gut check to make sure it is going to perform as you expect. Now, obviously, broadly speaking, there's a lot of points that you can find value of simulation. And I'm going to talk specifically on 2 conditions that we often see for these electrical enclosures and how you can use simulation to address these design and risk criteria. And those two specific criteria are related to thermal and structural reliability of your enclosure, which often is critical to the PCB and internal electrical equipment. At the end of the day, an enclosure is an enclosure, right? It's somewhat easy for us to redesign the casing if we're seeing failures there. On the PCB, that's not quite as difficult or as easy. It's fairly difficult once you've already got your board layout solidified and printed to make a modification to that board layout if needed. And so this thermal structural reliability of the PC ends up being very critical as we go through these design paths to ensure that you have that adequately determined before you get too far along with your design. And the reason that these are really critical, and I'll talk about the thermal here first, is that, as I mentioned, most components on a PCB are dissipating some amount of thermal energy. Now, oftentimes you have the dominant thermal generators. That's going to be any processing chips on your PCB. And because of that heat that they're dissipating, it can lead to a lot of either thermal stress on the board, and that can cause solder fatigue, or it could be that your components are coming up against warranty temperatures in their worst case ambient conditions. But what that means is that we have to investigate either passive or active cooling measures and determine which is the most applicable for our solution. And from a structural perspective, there's a lot of loads for abuse cases that you may need to consider, or fatigue conditions that can be difficult to assess and adequately prototype for, where simulation allows you to quickly, like I mentioned, iterate through those to ensure that you have that ability to not only withstand an abuse case, but operate reliability for the expected lifetime of your product. So often what this then means is we're taking active measures to design in structural and thermal mechanisms to manage these conditions, manage these fatigue loads or abuse case loads. And that could be evaluating different cooling mechanisms, again, passive cooling versus active cooling, or even liquid cooling if our thermal generation gets to too high of an extent to be managed from an air system. Or looking at some of a drop test or impact studies where we may need to add an additional PCB support, shock absorbers, or a buffer room within our device to ensure that there's not collision of components during these adverse events. Again, looking at protecting that PCB and the components on it at all costs. And what this means for electrical enclosures, because of that broad set of industries and applications, you have a wide variety of what these worst case scenarios or abuse conditions may be. But at the end of the day, we still need to make sure that regardless of what we're seeing there, we're getting into having reliable products that aren't going to exceed warranty temperatures or fail in the field at an earlier stage than we would expect or be advertising. Because the last thing that you want is have to be covering a large number of warranty claims for a product because due diligence wasn't done during the design phase there. And so I'll talk a little bit more in detail on each of these, and in particular, starting with the thermal design, right? The big thing with thermal design is, are we looking at active or passive cooling? And if it is active cooling, is it air cooling or some sort of liquid cooling form? And while there are some general rules of thumb for when you should look towards each of these, it's not very cut and dry. It's something that, analytically speaking, there aren't a lot of solid relationships that can give you a solid answer of, yes, passive cooling is going to be sufficient. And so as a consequence, it's often making a lot of gut checks or guesses as to what we should be doing based on prior product knowledge. But at the end of the day, that isn't always sufficient. We run into scenarios all the time where design is built based on the assumption that passive cooling should be sufficient when it's really not, given the exposure conditions and how much energy is being dissipated. And so simulation is an absolutely phenomenal tool towards addressing the need of active cooling, or if passive cooling is going to be sufficient. And if using active cooling, what's the extent of the active cooling? Do we need low-cost muffin fans that are low power, or a higher power muffin fan that's going to provide a very large amount of airflow over the chipset to adequately keep it cool? And if we aren't able to address these with active or passive cooling, you can get into thermal duration of components, right? This is pulling back the either the voltage applied, current going through it, or whatever be it, the processing capabilities of your PCB components to minimize the amount of heat generated during some of these adverse events. So let's say that you're designing a piece of equipment that's going on a 5G tower, and you want to make sure that it can withstand desert heat up to 45 degrees Celsius. It may not always be able to do that. So you're either adding in active cooling measures to make it withstand those high temperatures, or you're understanding that during those high temperatures, we're going to see a reduction in processing capability through thermal duration. And simulation can really help give you the insight necessary to know what's the probability of that happening And what is the likelihood of us seeing failures if we don't actively manage these components and go through some sort of thermal duration controls or have some type of active cooling on it? And lastly, when we're looking at thermal design, the solder fatigue potential is a large item for the potential implications on lifetime predictions, right? At the end of the day, you may have components that never exceed their warranty temperatures, but they cycle to a high enough heat frequently enough that it induces a lot of fatigue on that solder joint, right? The solder joint is expanding and contracting as it's heating and cooling. And so as a consequence, solder fatigue is a big consideration when we're looking at thermal design considerations. And you can see in the bottom left-hand side of the screen there that I've got this lifetime prediction chart. And you'll see this a couple of times. Simply put, if that line coming across that screen crosses the top bar first, that means that its probability of failure isn't adequate for our design conditions. So in this case, I've said I want a 95% chance that the product will survive for 10 years. But if it moves through that right-hand side to the green bar, that means that our product would be living long enough to not fail based on our design criteria. Now, you could realistically choose any probability of failure in lifetime based on your specific use case for your product. But these charts are really important as we're going through PCB reliability, ensuring that our systems, if we're implementing it into a car, isn't going to fail after a year of use, right? It's not going to be very sustainable from a practice perspective for an automotive developer if they're seeing failures of their onboard equipment every single year. So you want to design them with a lifetime in mind. And then on the structural side, oftentimes this looks a little bit different. It's a little bit easier for us to visualize some of those structural constraints. And so when we're considering simulation, a lot of times I like to say that we're really looking to design with confidence. When we do those simulations, we can clearly see where we have high stresses, for example, on a PCB, to make sure that we're adequately designing our device to minimize those stresses and reduce the likelihood of failure with it. And so oftentimes, as we're going through that structural analysis, it is making sure that how we have designed the equipment, how we have set it up, is going to be able to withstand that everyday use case and the abuse conditions adequately. And we know with confidence that it will. So when you have that individual who's installing your electrical enclosure in a data server rack, and they accidentally drop the piece of equipment, that's not just dead. That piece of equipment can be picked back up, installed right away, and that they don't have to worry about subbing it out every time something might happen or they drop a screwdriver on it, right? There's a lot of different conditions that we can look at. And so it goes past just understanding what exactly is happening during these conditions, but it also gives us information on what might be adequate damage, right? What are we tolerant of? Can we tolerate a crack on the enclosure? If so, what extent of crack can we tolerate? Can we tolerate strain on a PCB? If so, what's the extent of it, right? Simulation can help give you that insight to help determine what levels of stress or strain on different components is going to be tolerant for abuse conditions or everyday design scenarios for that lifetime prediction of our device. And past that, you can use this for both thermal and structural load reliability. So as I mentioned, you see that lifetime chart on the thermal side. You can do the same thing for structural design. So this could be shipping, making sure that your product is adequate or set up adequately to withstand any vibrational loads, or that if it's not able to withstand those vibrational loads, that it's packed in with appropriate packing material so that it could withstand those loads. Or even getting further to optimization of our product, right? At the end of the day, a lot of times when we're designing these systems, we may over-engineer components because we're not fully confident in its design function, and we don't have an analytical relationship that's easily built out to test that. And so oftentimes it leads to over-designing components, where simulation can really help pare that back, because you're getting to see and expose things to the exact worst-case scenarios you're expecting to see, minimizing the amount of over-designing that you'd need for it. And lastly, as I mentioned, you can use it to ensure that parts meet standards. So whether these are standards specifically for an electrical enclosure, for shipping, whatever be it, simulation can really help assist in that process to either directly meet that standard using the simulation itself, or ensure that when you're going into those tests to meet those standards, that your product is going to survive them and you're able to move forward in that product cycle. And so all of this is kind of placed out there arbitrarily for any electrical enclosure. And like I said, there's a lot of different applications and industries for electrical enclosures that have different requirements. And so I'm going to go through a case study of an electrical enclosure that we built here on the RANSIM side. This is an agnostic model that we use that's representative of models that we've seen in the past from a thermal management perspective. And for this case study, I'm going to go ahead and set in some design goals that I have. The first is that I don't want any of my chips to exceed warranty temperatures, right? This is an extremely common goal whenever we're looking at electrical enclosures. We don't want any chips to exceed warranty temperatures or any PCB components to exceed warranty temperatures. Additionally, I want to ensure that our product lifetime probability is at 95% at a 10-year lifespan. So that means that there is a 95% chance that my product is still working when it's been in use for 10 years based on my anticipated loading conditions. Now, again, this is a condition where you could choose anything you want based on your goals with your product design, but I'm going to choose this for this scenario here in particular. And then lastly, I want to ensure that my electrical enclosure, when dropped, would still be able to survive, right? It's still going to function, follow that. That way, if I do have an instance where this is dropped when it's being installed or when it's being pulled out for any maintenance, cleaning, the likes, that I don't have to worry about replacing it on warranty claims, that this product is going to have that survivability to manage that itself. And so getting into this, whenever we're doing these studies, you can start with the structural, you can start with the thermal. I'm going to start with the thermal here in particular. When we ran that initial baseline analysis to see how would my system perform, it was showing that temperatures on that PCB, specifically on those large thermal generating components on the bottom PCB, were getting really close to our warranty temperatures. You can see the two U chips there, we're getting up to 95 degrees, and then the A1 chip close to 60 degrees Celsius, where the A1 chip was actually exceeding the warranty temperature slightly, and the two U chips were getting close to it. And while in reality, this would potentially be tolerant from a maximum temperature, right? We could tolerate doing a small duration if our chipsets get to too high of a temperature in those worst case conditions to keep them below that warranty temperature. This had some dramatic implications on the lifetime prediction of our system, right? Because of that high temperature that both the U chips were getting to, we saw that our product would likely fail after about 7 or so years with 5% chance of failure rate, which was not tolerant to my specific design goals. So as a product, from my perspective as a designer in the system, I'm going to want to reevaluate how I'm going to be cooling the system. And we'll talk about that in a little bit here. But before we do so, I want to talk a little bit about that other condition, which is the drop test and the structural reliability of our component, right? And so here in the initial drop test that was done, it showed that in that baseline design, as it was initially configured, there was a large stress imposed on the center of the board. And realistically speaking, that was just because of how we had mounted our heatsink, right? We mounted the heatsink directly to the board, which at the end of the day probably wasn't the best decision there, but it meant that there was a fairly straightforward solution that we could implement into the analysis, right? We could go ahead and support that heatsink outside of just resting it directly on the PCB. Obviously still being glued to the PCB and its components, but allowing it to transfer some of that shock over to the enclosure as opposed to just directly onto the board itself. Because what this meant in this specific condition with these stresses it was being exposed to, the lifetime prediction for our product was closing in at only about 5 years based on a 95% probability. And so again, something that probably wouldn't be tolerable based on my design goals there, but it's letting me have that direct insight into what exactly is going to happen to my system when it's exposed to these conditions. So I can go into this and very minutely figure out what can I do to change my design to ensure that it works, right? I don't need to completely rechange my system. I can just add in some additional support material to make sure that that heatsink isn't directly applying its load during a drop onto the PCB itself and causing failures. And so what this means from a design modification perspective is two things, right? I have to address some of the thermal issues, and then I also have to address some of the structural response issues during the drop test. And so in this condition here, we could say that our product is being launched in about 2 months. So we don't want to make any massive overhauls. We don't want to have to completely reconfigure our heatsink or our PCBs, right? That's considered out of the realm of what we could tolerate from a time frame perspective. So we're looking at some relatively quick and easy substitutions. And so for a design like this, obviously substituting out those muffin fans to a higher CFM muffin fan would be a great way to start that process, right? Going from a fan that's getting approximately 10 CFM to the system to one that's getting about 45 CFM to the system. Sometimes you can do that with just a simple efficiency dump. Sometimes it requires some additional power. Since this is going to be directly mounted into a server, in this case, I'm not as concerned about the power requirements of the muffin fan in particular. I can easily ramp that up at the facility level. But that additional cooling mechanism would also mean that I don't maybe need to run my fan at the highest speed all the time, increasing the potential lifespan of the muffin fan itself. Additionally, like I mentioned, we'll add in some supporting material underneath the PCB, so that way we're directly supporting that heat sink as opposed to having to rely on the PCB to support the weight and inertia of that heat sink itself during an adverse event or abuse case scenario. So then I can take these design conditions and I can reevaluate my system based on them, right? In the baseline study, it showed that I had some risky temperatures for the A and U chips on my PCB with those 10 CFM fans. And this obviously, as we talked about, went in kind of didn't work the best for my lifetime prediction that I wanted. I wanted to make sure that I had that 95% probability at 10 years. And so going through that, substituting out that fan there, I was able to drop all of my temperatures on my components rather substantially by about 10 to 20 degrees Celsius each, which kept it well below some of those warranty temperatures. So no concern of need for thermal duration at that point. And in addition to that, it meant that all of my products went and met my probability of failure requirements, right? I wasn't seeing a probability above 5% at 10 years of lifespan. All those were falling well below that. So my product would meet my goals for my lifespan requirements. And this was all through just integration of that higher CFM fan, which is a fairly easy substitution to do in the simulation. So I was able to quickly get through this and now move forward with confidence that from a thermal perspective and from a solder fatigue reliability perspective, I was going to meet the product needs and not have to worry about any warranty claims for that reason as a product of it. And then on the structural side, I was able to go in and replace out or add in those additional supports. And this substantially increased the PCB's resilience because it wasn't going to be exposed to as high of strain. So you can see this here in the video showing that instance of the drop test right as the enclosure is meeting the ground there, and how the PCB on the left side, which is the original design, had a very high stress induced right at the junction of where that heat sink met the PCB. Obviously, deflections in this video are accentuated for visual effect, but on the right side, we're seeing a substantial reduction there, only seeing some higher stresses at the areas where the PCB is junctioned down. And if those were really a concern, I could add in some shock buffers to those locations, still keeping the PCB secure, but minimizing any transfer of shock loads directly to the PCB as a consequence. But as it stood, this was a big enough change for me to be confident moving forward, right? At the end of the day, this made it so my product wasn't going to see any adverse failures when it was being dropped. Additionally, I was able to use what I have here with my design to run it through an application called Sherlock on our side to analyze and make sure that it would meet MIL standard 810 requirements. That means effectively that my product is going to survive the shipping process, and it does so with nearly 100% reliability in that case. And lastly, I could assume that if my product was being dropped at some level of frequency, that its lifetime predictions are going to be substantially better with that updated design, with those additional posts supporting the heat sink, so that load isn't transferred to the PCB. Again, something that I was able to do because I could see directly in the analysis on how that heat sink was imposing a load to the PCB. In reality, that load probably wouldn't have cracked the PCB. So if I had done that drop test and done it as a prototype option, I wouldn't have seen a failure because that would only happen after 2 or so drops. But it's something that can happen with equipment. And it all depends on your design goals as you go into it. But this allowed me to see exactly where that loading condition was and create a simple fix to minimize or mitigate that issue as a likely occurrence. Like I said, increasing the probability of my product surviving for a longer period of time. And so overall, within this case study, really what we were able to do is take that initial design that had that lower flow rate on the fans, and despite the presence of the heat sink still not being able to dissipate enough energy to keep those products below the warranty temperature, and additionally make sure that my product, where we saw potential issues in the drop tests, had the appropriate design updates to not only minimize those risks on the drop, but also from a thermal perspective, ensuring that I wasn't going to be exceeding warranty temperatures. I wasn't going to be seeing adverse lifespans of my product, and that my design would be resilient for some of those adverse conditions. On top of all of that, my fans were then overcommitting from a power perspective, right? I was no longer having temperatures getting even close to the warranty temperature. So I could potentially reduce the speed of those fans to maybe even increase the lifetime of those fans themselves so that they're not running into their own reliability issues. And overall, I could take this and continue to move down steps, right? I could reduce the size of the heat sink because I have these new fans embedded into my design. I could go in and reduce material costs by, instead of having a stainless steel enclosure, potentially subbing that out for a lower cost plastic, or even shrink the footprint of the PCB if I had the time to actually do so, right? So these are things that I could do after I've even launched the product here, looking at a version 2 of my design where I'm no longer having to invest months of engineering hours to improve those efficiencies in the design. I already have the basis in simulation and I can quickly iterate upon that to bring a newer product to the point where it could be released at an earlier date within a year's time frame as opposed to 2 or 3 or whatever be it. And so overall, this shows how simulation can really be leveraged to not only enhance the process of a design of an electrical enclosure, but make it more efficient, make it more time expedient because of the ease of turning over these analyses in contrast to relying on physical prototyping, especially when lead times for physical prototypes are increasing as we go. And so overall, the conclusions for this entire webinar here are really that simulation is an effective tool at addressing design criteria and worst case scenarios while simultaneously ensuring that products can meet the desired lifespans as they are designed. At the end of the day, you can do some of these things with physical prototyping, but it leaves a little bit more up to the imagination because you don't get to see exactly what's happening within your system without a large integration of sensors that can sometimes impact the results themselves. So it allows for that ease of design iteration and moving forward and ensuring you have confidence in your design as it's going to be brought to market. And this is something that you can do in 2 ways. You can leverage the software that we use, right? We're an ANSYS channel partner at RANSIM, and so we're able to resell that software to anyone that may be interested in doing so. We use a couple different tools during this webinar, and we're happy if you have interest to walk through what exactly you're looking at and the issues you have to figure out what tools would be best fit for you. The other option is you can partner directly with us to do that from a service perspective, right? When we do services with our partners, and we do these oftentimes within the electrical enclosure space, we own that simulation process, meaning that we're not adding that as an additional burden to your process development or your project management sequence, right? We take in that work, we figure out what exact information is needed, and we either work with you or your suppliers to gather that data, helping reduce the total overhead to you. We make sure that as we go through this process, we're bringing in our experience that we have from other projects within electrical enclosures to make sure that we're taking into consideration some of the abstract areas where you see issues in these designs and helping make sure that as you move forward with your product design, you're really taking into consideration any potential risks that may be involved in that process. And lastly, when we do so, we operate as an extension of your team. This isn't something where we go, take it as a black box, solve a problem, and pass you back results. We make sure that you're involved in that discussion because at the end of the day, oftentimes if we have to make a modification to a system, that is going to have manufacturing implications. And as a product, we don't want to make that in isolation. We want to make sure that we're bringing you into those discussions. So we make sure that as we're going through those processes, those projects, we're bringing you into those discussions and we're operating as an extension of your team, making sure that we're all in it together to make sure we bring your product to a successful future for product development or for product launch.